Hello, good evening, sir. I will just start now. Um, I hope I'm audible and my screen is visible. Okay, so good evening once again, and welcome to this concluding session or a summarization session for the course on fundamentals of power electronics. So today we will be going through a summary of whatever has been taught in this entire course. So rather than a problem solving session, it would be kind of a recap session of the past 11 weeks. Of course, the 12th week is still going on, so I have not included that for today. We will see the problems for week 12 on coming Tuesday. I will be handling it on coming Tuesday. But anyway, so this is a summarization session for the entire course. So I'll just go through the basic concepts from each of the weeks and then, yeah, we'll just conclude it. Okay. I'll just turn on my charger just a second. Yeah. So okay, the summary is as follows. In the first week, we learned about the diode and basically we learned about the power devices. So diode is one of the first devices that we learned, and it is kind of an uncontrolled device. We learned about its power losses and how to calculate its reverse recovery losses. We learned about its power conduction loss as well as the switching loss or the reverse recovery loss. So then we came out to the BJTs, wherein we studied different configurations of BJTs, including the Darlington pair for increasing the beta value, right? And then we also went through the static and dynamic characteristics. And same was extended for MOSFETs and IGBTs and SCRs in week number 3, right? Wherein we again studied about the static and the dynamic characteristics and of course loss calculation. So kind of with week 1, week 2 and week 3, we studied most of the power devices that are used in power converters, including the uncontrolled diodes and the controlled MOSFETs or IGBTs and BJTs. So after we studied about the devices, we went through what is known as the first converter that comes to mind, that is the uncontrolled AC to DC converter, or popularly known as the rectifier. So we studied about the single phase half bridge AC-DC converter as well as a full bridge AC-DC converter. But one thing that we saw was that in order to have a stiff DC voltage at the output, we typically have a capacitor at the output. But it is seen that the capacitor draws a huge inrush current in order to charge up, because we know that the AC line cycle is kind of going to vary between 0 and 230√2 in our case at a frequency of 50 hertz. So what would happen is, since the input voltage is varying within 20 milliseconds, the capacitor would try to draw a huge inrush current in order to get charged up, right? And that is something that we don't want. So we did study about different kind of inrush limiting circuits or overcurrent protection circuits, correct? So after that, the basics of AC DC converters, we came over to the linear DC DC converters, also known as regulators, linear regulators, wherein we briefly studied about the shunt regulator and the series regulator, correct? And we also studied about their applications. Following that, in week 7, we came over to the switch or the non-isolated switched DC-DC converters or PWM DC-DC converters, wherein we have the popular configurations of buck boost and buck boost converters, and they are kind of non-isolated topologies, wherein you control the devices with PWM pulses. So instead of having drops across the BJTs or the regulators, here we kind of average it out. So we kind of get a switched waveform at the switching node or the AC node, and from there we put kind of a filtering mechanism or an LC filter mechanism to average the ripples out, right? So that was 7, and in week 8, we proceeded to DC-DC converters with isolation. So two of the most popular converters are, of course, the forward and the flyback converters, wherein we studied that the forward is a buck-derived converter and the flyback is a buck-boost-derived converter. Right. So after week 1 to week 3 was about devices, and then week 4 to week 5 was about the AC-DC converters and the interest current limiting in that. And week 7, week 6 was the linear DC-DC regulators or the shunt and series regulators. Week 7 and week 8 are the non-isolated and isolated DC-DC converters respectively. But one interesting aspect is that for both the non-isolated and isolated converters, we have either the inductor design or the transformer design. And of course, we know that these are being used in PWM converters that are switching at very high frequencies, maybe a few tens or even hundreds of kilohertz. So in that case, how do we design the inductor properly or the transformer effectively? So that is what we studied in week 9. That is about the design of transformer or the inductor, right? Magnetics design. And then in week 10, we proceeded to an improvement of the forward converter known as a push-pull converter, right? And from there, we also went through the half-bridge and full-bridge converters. We also studied a problem known as a flux walking problem, wherein the flux of the code slowly but very constantly goes on increasing or goes on decreasing towards saturation. And that's something we don't want. We also studied the problems to mitigate the solutions to mitigate the flux walking problem, right? So now that we had studied about all of these converters that are controlled by active power devices or semiconductor devices, so how do we drive these devices, right? So that is the next point, and that is where that is what we dealt with in week number 11. That is, we studied about the drive circuits for BJT and MOSFETs. We briefly went through what are the drive characteristics and what is the drive requirement for BJT and what is the drive requirement for MOSFET. And based on that, we kind of design drive circuits that can drive these devices. So week number 12 would be about closed loop control, but anyway, I'm not touching that right now. But just to give a flavor, closed loop control would be, the idea is that you want to regulate the output voltage because you may be driving an LED load or you may be charging up a battery. In that case, what you want is to regulate the output voltage to the set value. And in doing so, you also want to maintain the current. That is, you don't want the current to exceed a set value or go to a very high value that the devices may get damaged. So you have the current control and you have voltage control. And in order to do that, we take the help of control systems. So that is, we model the entire converter in terms of its state plane equations or the state equations. So we know that the converter is essentially made up of power devices and L, C, and R, right? So in that case, we know that for capacitor, the voltage is kind of stiff, and for the inductor, the current is kind of stiff. So if we can model how they are going to vary, then we can actually derive a mathematical model for the converter. And with the mathematical model, by applying linear control theory concepts, we can kind of design converters to regulate the output voltage or the output current or the load current or the inductor current. So that is something that would be dealt with in the next week. So that is not for today. So you'll see a recapitulation from week 1 to week 11. Okay. So just okay. So we'll start off with week 1. So week 1 was kind of pretty simple. We studied about the diode circuit, right? Ideally, we of course know that the diode is an uncontrolled device and it kind of operates in the second quadrant, correct? So let me take this as a point. Yeah, so it kind of operates in the second quadrant. So it can conduct current from anode to cathode, and it can block reverse voltage between cathode to anode. So if you give a positive voltage between anode to cathode, of course the diode is going to conduct. Okay. So from this we understand that it can operate only in the second quadrant, and of course it's an uncontrolled device. You can't control the current flow. Once the diode gets forward biased, it will start to conduct, right? Just that the voltage across the anode to cathode needs to exceed the cut-in voltage. If it does so, then it would start to conduct. Okay. So this is kind of an ideal scenario, but if we take a practical diode, so what we see is there is a specific cut-in voltage, maybe around 0.6 or 0.7 for silicon diodes and zero point 0.3 volts or 0.35 volts for germanium diodes. But anyway, so there would be a cut-in voltage, and beyond that, the diode would start carrying current. And of course, the diode is not perfectly lossless. It would have kind of a resistive impedance to that current. So the slope of this graph over here gives the dynamic resistance of the diode, that is delta V by delta I, that is this 1 by slope over here, right? Inverse of the slope. And it is also not that the diode can continuously withstand the negative voltage or the voltage between cathode to anode. So if we do apply voltage between cathode to anode, there will be some reverse current that would flow obviously, right, between cathode to anode. But beyond a particular point, beyond the rating of the diode would undergo an avalanche breakdown. So that is kind of known as a breakdown voltage, or the diode gets damaged and a huge current would flow through that. So that is what signifies the almost slope is equal to one line, right? So slope is equal to infinity line. Okay, so this is about a practical diode. But one of the important considerations is that in a diode, there is this problem of reverse recovery, right? So reverse recovery is due to the recombination of minority charge carriers across the junction, right? So it takes a specific time for the charge carriers to recombine and the barrier potential to form once again, right? So that is what actually defines the reverse recovery time for the diode. But unfortunately, what happens is because of this recombination, there is of course a reverse current, right, that flows from cathode to anode. You can see over here that there is a reverse current because of this recombination of minority charge carriers. There is a reverse current that flows from cathode to anode, right? And then once the reverse current dies down to zero, or once the barrier potential gets formed, this IAK current will gradually die down to zero. But unfortunately, we do have during this period, you wanted the diode to turn off at this instant, but unfortunately, there is a reverse current that flows over here. And associated with this is, of course, a reverse recovery charge, right? And this can be the cause for power loss in the device. That is the recombination of charge carriers is a cause of power loss in the device, right? So you can ideally approximate this to be a triangle. With that approximation, we have derived that kind of the reverse recovery charge is half into IRR into TRR. If you just approximate this as a triangle, you get half VH, and that is the QRR, right? So once you have a measure of the QRR, you know that the ERR is basically, that is the energy loss is half into QRR into VRR, right? So then once you know the reverse recovery energy, the reverse recovery power or the power loss will be energy times frequency. That is how many times this reverse recovery is going to happen in 1 second, right? Okay, so this is a problem with practical diodes, and of course, people have come up with solutions to reduce the reverse recovery problem for diodes, such as use of a Schottky barrier diode or so, right? Okay. So once we have studied about the reverse recovery, we studied about the power loss in a practical diode. So as we were mentioning just a while earlier, the diode can be represented as a resistance, that is the dynamic resistance, followed by a voltage drop. This voltage drop corresponds to the cut-in voltage of the diode. Okay. So if you just apply KVL over here, you get VAK equals VF, that is the cut-in voltage, plus IAK into RD, that is your total VAK. So once you know that, you can compute what is the power loss in the diode. So there would be a loss across this cut-in due to this cut-in voltage, and there would of course be the I square R loss due to this resistance. So we have just combined both of that, and we see over here that the total power loss is basically VF into IAK average, right? Plus IAK RMS square into RD. So mind you, or please remember that while you solve in problems as well, as we have done so in week 1, for calculating the power loss across a resistor, it is kind of a heat dissipation, right? So that is why we need to take the RMS current to calculate I square R, and to calculate the loss across VF, we can just take the average current. Okay, fine. So once you have calculated the losses, the next step is to attach a suitable heat sink, right? So that is where the thermal concentration comes into play. This is something that is done not only for the diode, but for all kinds of devices, such as the diode or the MOSFETs or BJTs or IGBTs. So based on your power loss calculation, we appropriately choose a value for the heat sink, and that is what we attach to the thermal pad of the device, so that there is better heat dissipation, right? Yeah. So approximated as the thermal chain can be approximated using the electrical equivalent circuit. That is, if let's say P loss is kind of a current source, that is the current flowing in this circuit, and Tj the junction temperature, then the temperature corresponds to the voltage, the R theta corresponds to the resistance in the circuit, and P loss corresponds to the current. So using that analogy, you can apply Ohm's law, and what you get is kind of Tj minus Ta is equal to the drop across these three resistances, right? That is P loss into R theta Jc plus R theta Cs plus R theta Sa. And since all of these thermal resistance are kind of in series, you can just add them up. Add them up. That is the total junction to ambient resistance would be the summation of the junction to case resistance, the case to sink resistance, and the sink to ambient resistance. Okay. So given any of these parameters, you can of course find out the other. So let's say they specify that the TJ should not exceed 120. Given your TA is 40, right? And the power loss is known. You just calculated the power loss on the previous slide. You know the power loss, TJ, TA are specified, and you will know from the device data sheet as to what is the junction to case resistance or the sink to ambient resistance. So then in that case, you can find out what is the unknown quantity, okay, using the thermal chain over here. Okay, so far what we have seen in diode, ideal diode, then a practical diode, then of course a reverse recovery issue, and then we learned how to calculate the power loss, right? That is the conduction loss when the diode is conducting, and the reverse recovery loss. Once you know that, you can calculate what is the heat sink requirement, okay, or the thermal conservation. Okay, fine. So let me just go over here and check once. Okay, so let me move on to the next week, that is week 2, wherein we went through control devices. So far the diode was an uncontrolled device. In week 2, we went to cover up the control devices or the BJTs over here, right? So as you know, BJT can operate in the first quadrant, right? So BJT can operate in the first quadrant, okay? So it can block positive voltage and it can conduct positive current from the collector to the emitter. And we know that the BJT is kind of a current controlled current source. That is, the base current controls your collector current and hence your emitter current. Okay, so the controlling parameter is your base current. So that's why it's a current controlled. And then it's a current source, right? Because your IC is dependent on what is your IB that you provide. That is, IC is equal to beta IB or HFE into IB, right? So this is the equivalent circuit of the BJT, right? So you have a voltage source VB, and you try to create a current IB by having a resistor at the base, right? So you have established a current IB. The current would be circulating through this path as shown in my laser, right? So once you have established IB, there would obviously be a collector current IC equal to beta IB. So since your value of collector current is fixed based on the base current, it can be approximated as a controlled current source, right? Controlled current source. So you would know that since it's a controlled current source, the symbol is like this. The symbol is like this if it's a controlled current source. If it was an uncontrolled or a free current source, you would have written it in a square or in a circular fashion like this. Okay, so there's a difference between both of these. So it's a dependent current source. It's a dependent current source. It's an independent current source. Okay. Yeah, so know the difference between both of these. So anyway, so you can approximate the collector side as a current source, and of course there is a cut-in voltage between base to emitter. There is a PN diode, there is a PN junction that gets formed between the base to emitter, and that is why we represent it as a diode here. Right? Makes sense, right? So you're taught by if you apply KCL, you know that IB is known, IC is known, therefore I is equal to IB plus IC, right? Or IB plus beta IB or beta plus 1 into IB. So if your beta is very large, right? If your beta is very large or IB is very small, you can approximate that IC is almost equal to IB. So that is some approximation we do in multiple places, right? Okay, so this was just about the equivalent circuit, and then with the BJTs, we studied about the regions of operation, right? That is, in a typical BJT circuit, as shown over here in your left-hand side, right? So as I told, you establish a current IB by having a voltage source, VB, and you have a resistor. So the path would be completed something like this, including the cut-in voltage. So IB can be approximated as VB, that is the voltage source provided externally, minus VBE divided by RB, that is the base resistance, right? So once you know IB, IC is beta times IB, so you know IC, right? And based on that, you can apply KVL over here, calculate VCE. So once you know what is VCE and you know what is IC, you can know where you are operating in the static characteristic curve, or where you are operating in the region of operation. For instance, right? So let's say IB was, there is some current IB, so IC equal to beta IB. So IC equal to beta IB, let's say, was at this point. Okay, you computed it. And secondly, apply KVL in this output side between collector to emitter. You know VC minus ICRC minus VCE equal to 0, right? So if you know what is your load RC and if you know what is your VCE, you get what is VCE. So based on that, you may be at the active region or in the saturation region or cutoff region. So typically in the cutoff region, of course, the device is off, right? And what you see is if you increase your base current, or the controlling drive current, your obviously IC would increase, right? IC is proportional to IB, IC is beta times IB, right? So you will have operate more and more in the active region, right? So this was about the static characteristics, and I will move on. Since VBE is kind of a PN junction, you will see that you get kind of a diode characteristic over here, and of course it is seen that it's a function of VCE. For higher values of VCE, the cutting voltage is even more, right? Okay. However, one unnecessary or undesirable characteristic is during cutoff condition, right? That is, during the cutoff condition, there is a small reverse current that flows. Okay, there is a very small reverse current that flows, and that is what we call as the leakage current. Okay, ICEO. Okay, but once you exceed the voltage rating of the device would break down, the device would get damaged, and obviously there would be a short circuit. So there will be huge current, even though you have not provided any base current now. That is, you wanted the device to be off. Since you have exceeded the voltage limit, there would be a huge current. Okay, that is something you don't want anyway. Okay, so after you covered the static characteristics, you went through the dynamic characteristics. So this is something that we went through in the last week as well while studying drive circuits, right? That is before yesterday. But here you understand that you start from over here, that IB was 0 previously. Then what you do in order to turn on the device, you will give a surge current of IB, and this is something we called as IB plus, right? While solving the problems. This should be about 2 times of your normal IB on. Then you come to IB on, right? So if you give IB on, then what would happen? there would be a current IC equal to beta times IB. Okay, and subsequently what would happen is you want to turn off the device. So in order to do it quickly, what you will do is you will apply a reverse current or a negative IB. So the base current would go negative, the device would turn off, and then you make the base current 0. So correspondingly, following this profile, your VC in IC also change. During turn on, IC increases from 0 to rated value, correct? And the VCE decreases from whatever the voltage it was blocking, that is VCC, to 0, right? Or VCE set. Okay, so this was about the dynamic characteristics, right? And what we told was there is a delay time, right? Delay time before which the current does not rise, and then there is the rise time of current. Okay. Okay. So our focus would be that during all of these regions, right, there can be power losses, because you know that the power loss basically happens only because of an overlap between voltage and current. In this case, overlap between VCE and IC can cause power loss, because VCE into IC will be the power loss across the device, right? So there would of course be the conduction loss when the device is turned on, right? That is VCE sat into IC average, correct? And then when the the device is turned off, you can almost approximate the power loss to be 0. Okay. Okay. So with this power loss calculation, again you can do heatsink calculation that I just showed with diodes. And one more thing was, okay, so inherently with manufacturing, you can only obtain a certain particular value of beta. You cannot obtain very, very high values of beta due to manufacturing limitations. So in that scenario, how do we increase beta? How do we obtain a higher beta? How do we obtain a higher current gain, right? Because the idea is with minimal base current, with minimal drive requirement, you want to get a high current, right? That is your idea. You don't have to strive too much to achieve that, right? So that is where we use kind of a Darlington connection, okay? So Darlington connection refers to kind of cascade connection of BJTs, wherein the output of the BJT2 will drive the power BJT1, okay, as shown over here. So if you do the calculations, you will end up with an effective beta of beta 1 into beta 2. That is, this entire thing can be considered as a BJT together. So there is the collector base and emitter. So across this entire BJT, you will get beta 1 into beta 2. And now you can obviously understand that if you increase the number of stages, you will get more and more beta, right? Okay. Okay, so after this, we went through MOSFETs, that is the next control device, and this is something that's being widely adopted for power semiconductors. But again, we followed the same template that was followed for BJTs and diodes, right? So first we went through the static characteristics, and interestingly, MOSFET is an improvement over BJT in terms that it can conduct in the reverse direction, right, between source to drain. And why is it possible? The reason is because there is, of course, a anti-parallel diode, right? There is an anti-parallel diode across your drain to source. Okay, so you can understand that diode being an uncontrolled device, what would happen is when you apply a positive voltage from source to drain, then the diode would turn on. So there would be a current flow from source to drain, and that is why it has a negative character, or a negative reverse conduction characteristic. So ideally, this is something that you see, that is, it can conduct current in both directions. So bipolar current conduction and unipolar voltage blocking. That is, it can block voltage from drain to source. You can understand that since there is a diode between source to drain, it cannot block reverse voltage, right? It cannot block voltage from source to drain because, of course, there is this diode. Okay, right. So this is kind of an idealized characteristic, but again, similar to BJTs, you will see that based on the drive over here, the current would also change. And this is something that's shown from commercial 1.2 kV 32 milliohm SiC MOSFET from Wolfspeed. Wolfspeed is one of the device manufacturers. So this is the VDS versus IDS curve, static VI curve. You see that with increase in VGS, with increase in the gate source voltage, right? With increase in the gate source voltage, the current also increases. Okay, so you can approximate the MOSFET to be a voltage controlled current source. Okay, that is the controlling voltage is your gate source voltage. So voltage controlled current source, right? So controlling voltage is your gate source. Based on that, the drain current will change. Okay. Yeah. So shown over here is the transfer characteristic or the transconductance as we call it. That is VGS versus IT. That is the controlling parameter versus the output parameter. Okay, controlling versus the output parameter. So the transconductance you can understand over here is basically the slope, and uh, it is the channel current of the drain current is given as K into VGS minus the threshold voltage the whole square. So you can understand that your gate source voltage, right? That is the drive voltage controls your ID. If you change your VGS, ID also changes. So that is why we call the MOSFET to be a voltage controlled current source. BJT is a current controlled current source. MOSFET is a voltage controlled current source, right? Okay. So after studying MOSFETs, we also studied about IGBTs, which is an improvement over BJTs and MOSFETs, correct? So the idea is, okay, the equivalent circuit is something that's shown over it is shown over here, and the idea is to have an insulated gate. Okay, so with that as the idea, what we see over here is we have three terminals, that is the gate, collector and emitter. If you control VGE, you control what is the collector current. Okay, but note that since this is a hybrid, you cannot have reverse conduction unless you have an anti-parallel diode. So most of the commercial IGBTs that are manufactured nowadays, they are manufactured with an external anti-parallel diode. Okay. So in MOSFETs, you have anti-parallel diodes that is inherent to the device. Okay. But with IGBTs, they are not inherent to the device package. Typically, you will see that nowadays people have provide an external anti-parallel diode provision. Manufacturers provide that. Okay, so this is about IGBTs, and finally, you also went through SCRs, right? So SCR, unlike MOSFET, it's kind of a dual form. It is kind of a dual of MOSFET. So in MOSFET, you saw that the MOSFET is a current bipolar but voltage unipolar device, right? It can block voltage in one direction, but it can conduct current in both directions. But SCRs can block voltage in both directions, but can conduct current only in one direction, right? That's a silicon controlled rectifier. You control the gate current over here, IG over here, right? So you would have, of course, studied that once you exceed what is known as the latching current, the device turns on, right? And in order to turn it off, you cannot just bring the gate current below latching current. You need to bring the gate current below a current known as the holding current and apply a strong reverse bias voltage. Only then it would turn off. Okay. And of course, the reverse conduction characteristic is similar to kind of your diode. So the idea you get is this is a voltage bipolar current unipolar device. Okay, unlike MOSFETs. And again, more your gate current, what you would see is you will easily turn on the device, right? It can reach latching current much faster, much easier with a smaller drop across it. If you provide less gate current, then there will be more loss, more drop across the SCR. It will lead to more losses for the device. Okay. So the idea is you need to provide enough latching current or much more than the you need to have much higher gate current so that the loss across the device is lesser, right? Okay, so this concludes our device part. Next, we will move ahead to the AC DC converters part. So I'll just pause here for 2 minutes. If you guys have any doubts, you can go ahead and ask, or I will just continue in a minute or two to AC DC converters. Okay. So till this point, we have seen about diodes, BJTs, MOSFETs, IGBT and SCR in brief, okay, about their static characteristics and dynamic characteristics, power loss calculation and heatsink calculation. We have seen problems in all of these. Okay, so this is about the MOSFET power device part. Next, we'll be jumping into AC/DC part. We will see about the AC/DC converters and the, of course, current limiting circuits. Okay, so yeah, I'll just wait for one or yeah. So IGBT VI characteristics, right? Okay, so you see over here, the IGBT is kind of a hybrid between ACRs, between your MOSFETs and BJTs. Okay, so the advantage you get, let me take my pen. Okay, so I'm not finding. So anyway, the advantage you get with BJT is that it's a current controlled current source. Okay, right? And with MOSFETs, you get that it's a voltage controlled current source. But the point is with BJTs, there is this problem that it can have a collector current only if there is a base current. So driving is difficult, right? That is, you need to have a constant current at the base. Only then there will be a collector current. Okay. So typically to drive BJTs, you need to have current source gate drivers, right? That is, current source gate drivers, as in like you need to maintain a continuous flow of current to the gate of the to the base of the device. Whereas for MOSFETs, you don't have that requirement. Okay, for MOSFETs, you just need to maintain a particular gate source voltage. So maintaining a voltage is easier because inherently there is this device capacitances. So you just need to charge up those device capacitances, right? And the device capacitances may be a few picofarads. Okay, so charging up that is much simpler and easier compared to maintaining a constant base current at the base of the BJT. Okay, so typically that is why people started to move towards MOSFETs. Okay, that is, the driving is much easier. That is, you just need to have a VGS. Okay, instead of having an IB. But the point is, if you have to go for high voltage applications, right? So for high voltage applications, it is found that BJTs can actually withstand very high voltages. Okay, MOSFETs are not rated for high voltages. Even today, you will see commercial MOSFETs are somewhere around 1.2 kVs. 1.7 kV MOSFETs have, of course, some people have started researching on 3.3 kV MOSFETs, but you can understand most of the commercial available MOSFETs are limited to the range of 1.2 kVs. So that is where IGBTs come into play. That is, can you take the advantage of BJT in conduction and the advantage of MOSFET in gate driving? Okay, advantage of BJT in conduction and the advantage of MOSFET in gate driving. So that is where we get what is known as the insulated gate bipolar transistor. So, right. So let me draw over here as well. Yeah. So what you have is, let's say, you have something like this. So this is your collector. This is your emitter. This is your power side. Okay. But I don't want to feed a base current. Okay. I don't want to feed a base current. What I will do is I will just want to feed a pulse VG. I just want to feed a pulse VG. So how do I then complete the circuit? Okay. So then what I can do is I can feed this pulse to a MOSFET. Okay. With MOSFET, you know that there is the advantage that the MOSFET, in the MOSFET, the gate is kind of insulated, right? It's kind of an isolated gate. It is an insulated gate. Okay. Secondly, as I told, MOSFETs require voltage source gate drivers, not current source gate driver. So I will control a MOSFET or I will drive a MOSFET, and this in turn, so once I turn on this MOSFET, okay, once I turn on this MOSFET, somehow I will try to establish a current through this MOSFET to the base. Okay, so I will establish a current indirectly, not directly. Okay. So if I can realize something like this, of course, there will be a, I should not be drawing like this directly, there will be a power source over here. So if I can realize something like this, right? So then what we are getting is we are having a base characteristic similar to MOSFET, right? Base similar to MOSFET, okay? And the collector to emitter similar to BJT. That is why you see the terminals being named as collector and emitter in the power side, but gate in the driving side. Okay. So because you are giving the gate pulses to the gate of this MOSFET only, not to the BJT directly. Okay. Okay. So with this information, of course, you know that the output characteristic will be a VCE versus IC, right? VCE versus IC. Okay. So in that scenario, you can understand that since what you are having over here is simply a BJT, right? What you are having over here is simply a BJT. You can understand that you will again have characteristics similar to a BJT. Okay. The only difference is that since you are giving a gate pulse, what you will see is in normal BJT, this would increase with IB, right? That is, we saw something like this, correct? With increase in IB, the curve is also shifting up. For IGBTs, you will see that with increase in VGE, this curve is shifting up. Okay, because the controlling parameter is not the base current, it is your gate source voltage or the gate emitter voltage. Okay. Oh. Yeah, so I hope it is clear now. So over here, you see that in the power side, you have the BJT, and for the driving side, you have the MOSFET. So that is why you call it as collector, emitter in the power side and gate in the driving side. So the VCE IC characteristic is somewhat similar to your BJTs. Okay. But the only difference is that as your gate emitter voltage increases, it will change. In BJTs, as the base current increases, it changes. Okay. That is the difference. Okay. Okay. So we will move ahead with diode bridge rectifiers now. Okay. So here we will be a little bit faster because we already know about these. That is, you have for single phase uncontrolled half wave, you just have the AC source. We have a diode over here and connected to a load. You know that the diode will be turned on or it will be forward biased when during the positive cycle of voltage, and during the negative cycle, of course, it will be reverse biased. So the output voltage will be clamped at zero. Right? So this is your output. So the output voltage will be clamped at zero. Okay. And in case of a full wave, you can have kind of a bridge topology. What you will see is the opposite diodes or the diagonal diodes will be conducting together. Correct. So D1, D2 will conduct over here, and D3, D4 will conduct over here. Okay. During the positive half cycle, automatically D1, D2 will be forward bias. So V0 will be equal to what? Just your AC line cycle. And during your negative cycle, D3, D4 will be forward bias. Therefore, your V0 will be the rectified or the inverted version of your line cycle during this period. So this is getting inverted. Okay. However, you understand that this is something that cannot be fed directly to any load, right? A DC load would ideally want to have a stiff DC voltage across it. Let's say you want to drive an LED load, or you charge up a capacitor, or you charge up a battery, you would want a stiff DC voltage. So in that case, let me check if my screen is visible. Okay. So in that case, what we do is we typically add a capacitor over here, and the capacitor is rated for a very high value so that it maintains a stiff DC voltage. So what you can understand is when your, let's say under steady state, if your capacitor is already charged to this much, right? Your capacitor is already charged till a potential of this, then what would happen is that once your input voltage exceeds beyond the capacitor voltage, the capacitor would obviously charge up. Okay, the capacitor will charge up. So that represents the interval between the two red lines. Okay, so because the capacitor is charging up, it will draw a huge current or it will draw a peaky current during this interval. And of course, when the automatic rectified voltage goes below your capacitor voltage, the capacitor will discharge to the load and therefore the capacitor voltage will slowly drop. Okay. So you basically have two areas over here or two intervals over here. That is, this is your capacitor charging interval and this is your capacitor discharging to the load. Discharges to the load. Okay. So as I was telling, when the capacitor charges up, it will draw a peaky current. Okay, so because there is no impedance in the circuit, it will draw a peaky current. Okay, and of course, during the interval of capacitor discharging, it will slowly discharge to the load according to the load requirement. Okay, so if your capacitor value is lesser and lesser, you will see more and more fluctuation. It may be even something like this. Okay, if your capacitor value is lesser. Okay. Okay. So this inrush current is something that you don't want because let's say during the starting, the capacitor is totally uncharged, right? So when the capacitor is totally uncharged during starting, so let's say the line voltage is something like this during start and the capacitor is also totally uncharged. So what would happen is the capacitor will draw a huge current. Okay, capacitor would draw a huge current because the capacitor will also try to charge up something like this and then it will go over here. So during this interval, the capacitor would be drawing a huge current, much higher than this, maybe even 10 times higher than this. So it can damage your components and that is something you don't want, right? You don't want this. So that is where we study about inrush limiting circuits or limiting the inrush current. Okay. So how do we do that? We have multiple solutions for that. We went through that in the lecture slides. So one solution is to use what is known as a surge limiting resistor. Okay, that is in order to limit the current, add a resistor at the input side, and you will read the resistor for the surge current. Okay, so in the data sheet there is something known as the non-repetitive peak current of the diode. That is, the diode can withstand a peak current for a very small interval. Okay, just once. So you will rate the resistor for that current so that that current is not exceeded. Okay. So obviously your resistor, the minimum value of resistor that you need to have would be the peak value of your AC input current. Okay, peak value of your AC input current divided by that limit. So that should be the minimum resistor you need to have. You need to have more than that, obviously. Okay, so this is one, that is you add a resistor, but you can understand that this is something that is lossy, right? And there will be a drop across this resistor every time. So the effective voltage seen over here would be lesser than VI. So VI is something, but I will see only VI minus I in RS, right? So the effective resistor, effective voltage is obviously low. So that is something you don't want. Okay. So instead of the surge limiting resistor, can I make this a variable resistor, right? So that is when people came up with what is known as the thermistor, wherein the resistance changes with temperature, right? So as your temperature increases, then the resistance obviously decreases. Okay. So this is what people came up with next. That is to make sure that in steady state, we don't want this resistor coming into play. We would want it to provide very little resistance. Okay. And then people came up with an isolation mechanism. Okay, so there is a peaking current over here. What can I do so that this surge doesn't get transmitted to the output side? Okay, so that is when people came up with a transformer based solution. So since you have an isolation between the input and the output, obviously the surges over here will not get reflected over here. Okay, but what is generally used is basically this active device. Okay, active device, and next also you'll see, but anyway, this is very widely used or popularly used. Okay, fine. So what are we doing over here? Um, So instead of connecting this to the ground point directly, we connect it to the ground through a MOSFET. Okay, we connect it to the ground through a MOSFET. And we control the MOSFET, based on the output. Okay, why? Because we saw that during starting, right, let's say this is your AC line cycle, and your capacitor voltage would be something like this, and then it would slowly go over here, and then it would be like this. Okay, so the problematic part is this, right? The problematic part is this area, correct? That is, there is a huge peaky current that's going to flow. So what I can do is, if I detect that the voltage is lesser, correct, I will simply not enable this path. If this path is disabled, there is no path for the current to flow, right? There is no path for the current to flow. Okay, so that is why what I do is I will have a series MOSFET over here, and this MOSFET will get enabled only when the output voltage reaches a particular value. Okay, so we have a capacitor at the gate of the MOSFET. Okay, so this capacitor is being charged by the output voltage itself. We take a tapping from the output voltage and give it to this capacitor. You know that the MOSFET can turn on only if this capacitor charges up, correct? That is, only if VGS more than V threshold, the MOSFET will turn on. Okay, so I will slowly charge up this capacitor so that the MOSFET doesn't turn on in the starting period. So the MOSFET capacitor will slowly go on increasing. Okay, and you know that in any MOSFET, as your VGS is lesser, if your VGS is lesser, the RDS is high. Okay, so we can also see, we also saw that in the MOSFET characteristic. That is, if your VGS is less, RDS is high. So even if this MOSFET turns on, it would provide a high impedance path. Okay, it would provide a high impedance path. So this would be a high impedance path, and as your voltage goes on increasing, as this voltage goes on increasing, the resistance will go on decreasing. Right? Makes sense, right? As your voltage, as your capacitor voltage over here, which is reflective of your output voltage, as this goes on increasing, the RDS goes on decreasing. Okay, so the resistance goes on decreasing. Resistance goes on decreasing as this voltage goes on increasing. So, and as the resistance goes on decreasing, the capacitor will get charged up more and more. Since you have a resistance over here, the inrush current is limited. Okay, so we are limiting the inrush current based on the MOSFET RDS on. Okay, and how do we control the MOSFET? We control the MOSFET based on the output voltage. We take a tapping of the output voltage, and then the output voltage is only used to control the MOSFET. So if your output voltage is lesser, the capacitor will of course try to draw a huge current, but anyway, if the output voltage is lesser, the MOSFET will be somewhere here, the RDS is larger, so there is a impedance path over here, therefore the inrush current is limited. Okay. Okay, so it's a variant. This is just a variant of the previous circuit. We take a tapping from the input itself, we rectify it separately, and then give it over here. Okay, so this was using MOSFET. Okay, right. And finally, or the most commonly used method in any commercial device that you will see is based on relay and contactors. Okay, that is, you can have a relay mechanism. So just in a nutshell, you will sense what is the output voltage. You will take a tapping, sense the output voltage, and compare it with some threshold voltage. Okay, you will compare it with some threshold voltage and use it to close a relay. Okay, so what you will do is you will sense whether the output voltage has risen up. If the output voltage has reached the rated value or near the rated value, then this contactor will close. Okay, if the output voltage has reached near the rated value, then what would happen is basically your plus terminal will be more positive than your negative terminal, right? V plus more than V minus. So this is a comparator circuit. So since V plus is more than V minus, the comparator would go high. So if your comparator goes high, the BJT turns on. If your BJT turns on, this inductor or this coil is going to get energized. If your coil gets energized, then this switch will complete the circuit, it will turn on. So if your switch turns on, then this relay is going to get energized, right? This relay will get energized. If your relay gets energized, this contactor is pulled. Okay, this contactor is pulled and the circuit is connected. If not in the initial stage, if your voltage is lesser, then obviously the output of comparator is low. So BJT is not energized, therefore the switch is open, the coil is not energized, switch is open. So this contactor is also open. So obviously there is this high impedance path. So the induced current is limited. Okay. So basically you are having this you are having this interest current limiter during the starting part. Okay, you are having this interest current limiter during the starting part. And once you reach the rated normal steady state operation, you bypass the high impedance part using a contactor. Okay, this is the most commonly used mechanism, right? And you also studied about the three phase uncontrolled rectifier. You get a 6 pulse within a line cycle, right? Okay. Okay, so this was about the AC/DC converters. I'll just pause over here if you guys have any doubts, or we can start off again at 7:10 from linear DC/DC converters. Okay. Okay, so I'll just continue from over here, right? So till now you have seen the devices and then the AC/DC converters. We saw about limiting the inrush current. Okay. Okay. Um, yeah. So from now on, we will see about linear regulators, right? So that is okay. So we have used the AC/DC converter to get a stiff DC at the output of the AC/DC converter. But from there, how do we get a regulated DC output, right? So we know that the output of a AC/DC converter is kind of uncontrolled, right? So we don't have any control over that if we don't use ECRs. So with that, how do we convert it back to low voltage that is required for charging up the battery, right? So we have a DC at the input and we want to charge it with a stiff DC at the output. Okay. So for that, one of the approaches is to use what is known as a linear regulator. Okay. So we have two kinds of linear regulators, that is a shunt regulator and the series regulator. Okay. So first we see about a shunt regulator wherein we use the reverse characteristic breakdown property of a Zener diode. So the Zener diode obviously operates in the third quadrant of the diode, wherein you get a fixed VZ, right, irrespective of the load current. Irrespective of whatever is your IZ, you will get a fixed VZ. That is the characteristic feature of a Zener diode in its breakdown region, right? Of course, you can't have a huge current flowing over here. There would be some rating that's specified in the data sheet of the diode, but you can have variation in current between IZ min to IZ max, but your load voltage or VZ is maintained constant. Okay, so your V in is not pure. It can vary from V in max to V in minimum to V in max, right? So based on that, your I in will vary, but based on that, your IZ will vary, and your R naught may also vary from R naught min to R naught max. But how do you maintain V naught constant? Okay, so that is where your shunt regulator comes into play. That is with the Zener, the characteristic, you maintain a fixed VZ irrespective of your load current, right? Okay, but that was with an ideal Zener, but with a non-ideal Zener, you see that the breakdown voltage is not constant, right? It would be having a slope that is that depends on your IZ. Ideally, you don't want VZ to depend on IZ, but what you see over here is that you have the VZ increasing with your increase in IZ. So that is something you don't want, right? So now that you incorporate this loss component of RZ in the equivalent circuit, what you will see is that the V naught by simply KVL, you see that V naught is equal to VZ plus IZ into RZ, right? So this term IZ into RZ actually results in a loss of regulation, and that is something we have to reduce in order to improve regulation. If you want to have a stiff output voltage, right? You want to make V naught equal to VZ. So somehow we should compensate this, right? That is the non-ideality of a Zener diode, right? So this slope is your 1 by RZ. Okay. Okay. So that is where we use a BJTs over here. This is the modified shunt regulator. Instead of having this as directly the output voltage, can I have some element over here, right? And this can just be a driving force for that element. At the output of that element, I will take the output. For example, see the combination of the Zener diode over here is just to drive the base of the BJT, and at the output of BJT, I will take V naught. Okay, because you know that I naught is basically over here the base current controls what is your collector current and hence your emitter current. So if you apply KVL over here, you will get V naught is equal to VZ plus IZRZ minus VB, right? And you know that your IZ will be very, very small, right? Because your base current is also going to be very small. So your IZRZ is going to be much, much lesser. Okay. So you will get almost a stiff voltage V naught. That will be VZ minus VB almost. Okay, because your IZRZ is much, much lesser. Why is your IZRZ lesser? That is because the load current, that is the base current, is very, very less for a BJT. Since your base current is less, Iz will also be less. So if your Iz is less, IZRZ is less. Okay, just a small modification. We just added a BJT over here, made this drive a BJT. So your load current is less, base current is less, so your Iz is less. So IZRZ is less. Right? Okay. So what are the applications of such a circuit? So we have seen two applications. That is, it can be used to provide a fixed voltage reference. This is the same circuit redrawn in a different fashion, but you can understand that you can obtain a fixed voltage reference, and if you have a pot over here, you can vary the turns ratio of the pot and get a different Vref. So that is your voltage reference. But secondly, or more importantly, you can get a current regulator. Okay. So by this, again, this is a redrawing of the previous circuit that we just saw. So with that, you get kind of a current regulator. Okay. Again, in order to solve such circuit, you just use basic principles of KVL, KCL, and know that IB equal to or IC equal to beta times IB. With that, you can get whatever is required. Okay. So here a PNP is used instead of NPN. So over here, you replace this NPN with a PNP, right? And you reconfigure the circuit, you'll get this. Okay. Okay. So as I told, you don't need to remember or mug up any of this. You just need to apply basic KVL, KCL, and you know that IC equal to beta times IB and stuff. So you can just solve it easily. Okay. So once you are done with shunt regulator, right? So shunt regulator, we have seen what is a shunt regulator with an ideal Zener diode, with a practical Zener diode, and we modified it, included a BJT to remove the IZRZ term, and we saw two applications, that is to provide voltage reference and to provide current regulation. And the second one that we saw is about the series regulator, right? That is okay. So if I have a resistor over here, I can vary this resistor based on the requirement, and I can vary this resistance so that I get a fixed V naught. Okay. And we can have kind of a closed loop regulation over here. That is, if your V naught increases, then the feedback over here V naught is going to increase. So V naught ref minus V naught is going to decrease. Therefore, your RS can be increased, right? There will be more drop across RS and V naught will be reduced, right? So you understand that RS is kind of a lossy term. It's a lossy resistance. So instead of RS, we can have a BJT and control the VCE drop across the BJT, right? So you can have a BJT over here and control the VCE drop. I will control the VCE drop. And if I control the VCE drop, I can control what is V naught, right? So again, we take a feedback mechanism. So you take a tapping of V naught, that is a V naught over here, you use it to drive Q2. Okay. You can use that to drive Q2, and if you drive Q2, based on that, your driving current for Q1 is going to change. If your driving current for Q1 changes, the drop changes. Okay. Okay. So what is the procedure that is adopted over here? Look at this circuit. That is, your IRB over here is kind of always constant, right? Why? Because VI minus this voltage is basically V0 plus VB1, right? Divided by RB. This is your current that flows through IRB. Okay. So this current is kind of constant. So if you apply KCL at this node, then what you get, IRB is equal to the collector current of Q2 IC2 plus the base current of Q1, okay, IB1. So if your IRB is constant, if IC2 increases, IB1 has to decrease, or if IC2 decreases, IB1 has to increase. So how is IC2 related to your V0? Simply over here, you can understand that let's say V0 increases, right? If your V0 increases, you wanted to have a stiff V0, but your V0 has increased. So in that case, your V0 has increased, so your AV0 has increased. If your AV0 increases, then what would happen is the base current over here, right? Q2 base current of Q2 IB2 increases. If your IB2 increases, IC2 increases, right? Because IC2 is beta times IB2. So IC2 increases. If your IC2 increases, then IB1 would obviously decrease. If your IB1 decreases, then there will be more and more drop across Q1, right? Because we have seen for a BJT, if your base current or the driving current is lesser, the drop is going to be more. Okay. So your base current decreases, therefore VCE drop increases. If your VCE drop increases, V0 will decrease. Just by KVL, V0 will decrease. So this is kind of a automatic feedback mechanism that you have. Okay. Right. So you just took the tapping, you control what is the collector current and hence what is the base current for Q1. If you reduce base current, the drop increases, therefore V0 again decreases. Okay. Right. And with this series regulator, we also saw how to implement a negative voltage regulator. So the negative voltage regulator is just a dual of the positive voltage regulator. Replace NPN by PNP and reverse the polarity of the Zener diode. See, the polarity of the Zener diode is reversed and replace NPN by PNP. Right. Of course, the input will be negative. So once you have both the positive and the negative voltage regulators, you can combine both of them on a same rail, that is the 0 point or the ground point. And with respect to that, you can have both a plus and a minus. Okay, so if you have plus 15, minus 15, you can get plus 10, minus 10 by using these regulators. And these are very commonly used in ICs nowadays. Okay, all of this is integrated monolithically within an IC. Okay, so you can get a dual power supply linear regulator. Okay, fine. So I hope linear regulator is fine, right? We have seen what is the series regulator and the shunt regulator. Shunt regulator, its applications, and series regulator, right? How the closed loop mechanism happens, right? If how the closed loop works out, and then based on that, the application would be the negative voltage regulator and dual power supply linear regulator. Okay. Fine. So this was about week 6, right? Now we will move on to week 7. Okay, that is about the switched mode converters, right? So just a second. Just give me a minute. I'll just have some water. Okay. So in week 7, we went through switch mode DC-DC converters, right? So that is, we can have switches over here, and what we will get is we'll be chopping the input voltage continuously. Okay, that is VI0, 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 and I can of course control what is the turn on and turn off time of the switch. So if I control what is the turn on and turn off time, I am essentially controlling what is the period for which VI appears. But you can understand that this kind of a chopped voltage cannot be given. This kind of chopped voltage cannot be given to any load directly, right? So what you would want is a stiff DC voltage. So in order to average it out, we have to have some filtering mechanism in order to average it out. But once we do that, then what we can get is with just using power devices, we can get a fixed average voltage. Okay. So the turn on period with respect to the total period is what is known as the duty cycle, okay, or the duty of the device. Okay, so shown over here is a typical realization. That is, what we can do is we can have a single pole double throw switch. If the P pole is connected to throw 1, right, then V in is directly connected to the output. Okay, and if the pole is connected to throw 2, then the output is connected to ground. Okay, that is how we switch between V in 0, V in and 0. And in order to average it out, we can have an LC filter over here. Okay, so we will have an LC filter over here that will average out this continuously switch node waveform. Okay. Okay, so here in order to design these L and C values properly, we have to understand about these inductors and capacitors first in a power converter. So for an inductor to operate at steady state, it has to satisfy what is known as the flux balance or the old second balance. That is, you know that VL is L into di by dt. So in average state or in steady state, the average voltage across an inductor should be 0, right? Or there should not be any net flux increase or decrease across the inductor. It should be operating at a particular point in the BH curve. Okay, so let's say the BH curve is something like this, correct? So you will be operating, let's say over here. Okay, so you will be operating at a particular point in the BH curve. You don't want to move on up and up and you will saturate. Okay, you don't want to go near the saturation point. Okay, so what you would want is the net flux in a cycle should be 0. Net flux should be 0. Therefore, it should not gain flux or it should not lose flux. The net flux will be 0 within one cycle. Okay, so that is why we tell that the average voltage should be 0 or integral V dt should be 0. Okay. Similarly, for a capacitor, you can understand it would be a dual of that. So you have to have what is known as the ampere second balance or the charge balance in a capacitor. That is, the capacitor should not gain net charge or it should not lose charge within a cycle. The net charge should be maintained constant in steady state, not during transient. Of course, during transient it will change, but once you have reached the 50 volts limit or something like that, it needs to maintain at 50 volts. So there should not be any net reduction in charge. There should not be any net gain in charge. Okay, that is why integral IC dt should be 0, and this is coming from the first principle that IC equal to C dV dt. Okay, so this is what is known as your charge balance. Okay, so with that information we have gone through. I'm not going through the entire elaborate waveforms for each of these, right? But you of course realize that with this you can implement what is known as a buck converter, right? So we have seen about the primary, about the VP, right? That is the pole voltage. And then we saw what would be the inductor voltage. When the pole is connected to through 1, then the inductor voltage would be V in minus V naught. And when the pole is connected to through 2, inductor voltage would be minus V naught. That is why Vi minus V naught during DTS interval, minus V naught during the 1 minus DTS interval. And if your inductor voltage is positive, then what would happen? We know V is LdI by dt. You know that P is equal to LdI by dt. So if VL is equal to positive, then di by dt is positive, correct? So IL will increase, correct? And vice versa, if VL is negative, what you will see is di dt is negative, therefore current, inductor current will decrease. Okay, so inductor current will decrease. So that is why you see over here the inductor current in steady state. Inductor current is kind of increasing during the DTS period and decreasing during the 1 minute period, and it continues. So this is the inductor current, and you can understand that the inductor current is basically composed of an average component called I naught. Since the inductor is towards the load side, the average current is I naught, and there is of course the ripple component of delta IL. So you can understand that a capacitor ideally blocks DC, right? Capacitor will block DC. So it cannot take this average current, it will take only the AC component. Okay. You know that a capacitor, impedance of a capacitor is basically XC is equal to 1 by omega C. Okay. So XC is equal to 1 by omega C. So you know that for DC at omega equal to 0, impedance is infinity. So the capacitor blocks DC. But of course, it can take the ripple component. The ripple component is AC. So that is why you would have learned that the capacitor current is simply the delta IL current, not the I naught component, just the delta IL current. I naught component will flow through the load. So two purposes are satisfied. That is, I naught is maintained. The I naught will be a maintained DC constant. The capacitor will absorb the ripple and will also maintain the voltage, right? Okay, so you saw how to rate these IT1P and IT2P. What is the voltage blocking across VT1P and VT2P, right? You need to rate it for the input voltage, and of course, you know that you need to rate T1P and T2P for the maximum current or the peak value of the inductor current, right? Okay, so first of all, you studied about how to obtain a particular value for L, right? That is based on the ripple requirement. If they tell that the ripple requirement is 10% or 10-20%, or based on that, you will compute what is the value for L, right? Again, the computation is simply based on LDA by dt. V is equal to LDA by dt. Simple principles. You need not remember this formula. Just you should know V is equal to LDA by dt. Okay. And during DTS period, dt is equal to capital DTS and VL is equal to V in minus V naught. So you just substitute that over here, you will get what is delta L or delta L. Okay, simple, right? V is equal to LDA dt principle. And similarly for capacitor, I is equal to C dV by dt, correct? You apply charge balance over here, right? So C into delta V, C into dV is equal to I into dt. I into dt is basically the area, right? So we just drew the capacitor current. If you find out what is the area, what is the net positive area or what is the net negative area, if you find out the positive area or the negative area is basically what? Current into time, right? That is the charge, right? So that is why we have written it. If you find out the area, it is simply half BH again. So half into delta L by 2 into TS by 2. So if you do the calculations, you will get something like this, right? So in both of the cases, you obtain that using V is equal to LDA dt, I is equal to C dV dt, right? C dV by dt. And you just need to know what is the current through the capacitor and what is the voltage across the inductor, right? From that you can find out, just compute the area that gives the charge, right? And for inductor it gives the volt second. V is equal to LDA dt, I is equal to C dV dt. Simple, right? So again, you need not remember all of this, but one characteristic feature is, you note L is inversely proportional to Fs, correct? If you take L to the other side, L is inversely proportional to Fs. Similarly, C is inversely proportional to Fs. Okay. So if you increase your switching frequency more and more, you can reduce the value of the filter elements. So generally in a power converter, you will see that the filter elements are the ones that take up a huge size. Okay. So if you increase the switching frequency more and more, if you let's say go from 10 kilohertz to 100 kilohertz, then your L and C values are going to reduce by a factor of 10. Then if the requirement reduces, the size of LNC are also going to reduce. Okay. So your values of LNC will reduce based on your switching frequency. Correct? Okay. So as your switching frequency increases, you can have lesser and lesser values of LNC. Okay. So specifically, you also saw how to design for your values of switches for VT1P and VT2P, IT1P and IT2P, correct? And based on that, you can recognize in what quadrant the devices are going to operate. Okay, so turns out that the pole between VT1P can be realized with MOSFET or IGBT or BJT because it has to block positive voltage and it has to conduct positive current. Whereas if you see from T2 to P, right? If you see from T2 to P, you need to have a diode because it needs to be a negative voltage blocking between T2 to P and it should conduct positive current. Correct? So that is how we realize that. But not only this buck converter, you also have multiple combinations. Correct? You can have multiple configurations. For instance, in the same converter, if you plug out this L from the output side and you plug into the input side, you get what is known as a boost converter, right? This is just a different combination. And you also have what is known as the buck boost converter. That is, you interchange the places for the inductor and the switch. You get the buck boost converter as well. And you of course have gone through realizations for that, correct? It is realized something like this with poles and throughs. Okay, so in a buck converter, the point is you always have an output voltage which is lesser than the input voltage, correct? Output voltage is always lesser than the input voltage, right? And since the output voltage is less than input, the output current will be more than the input current, right? Because your power balance needs to be maintained, correct? So this can be somehow called as a DC-DC transformer, right? You obviously don't have a DC transformer in real life due to saturation issues. You cannot operate transformer at DC. But what you are seeing over here is you have stepped down a voltage, input voltage from high input to a low input, to a low output. Okay, and you have stepped up the current from high input current, low input current to a high output current. So it is kind of a step up, step down operation that's happening for the voltages and currents. So it can be called as a DC transformer. You are basically realizing a DC transformer with power electronics. Okay, and with boost converter, you can have a higher output voltage than the input voltage. So you can understand higher output voltage means lower output current than the input current. And with a buck boost converter, you can have both in both buck and boost operation. That is, you can the output voltage can go above or below your VI, right? So that is your advantage. And one more thing is, since inductor is a current stiff element, right? Inductor is a current stiff element. If your inductor is in the output side, the output current is continuous. If your inductor is in the input side, the input current is continuous. Input current that you draw from the battery will be continuous. And output current that you give to the load will be continuous for a buck. Okay. For buck, the output current is continuous. For boost, input current is continuous because inductor is in the input side. For buck boost, it is neither, right? Inductor is neither in the input side nor in the output side, so neither is continuous. So if you go to advanced courses, you will see that there are converters which can give you continuous input current, continuous output current. So you can understand there needs to be inductor in the input side and inductor in the output side. Okay. So this is a requirement for applications like batteries. So let's say you are using a buck converter, right? You want to have a buck operation. You are having a high voltage battery. You want to charge up a low voltage battery, right? So in a buck converter, you can only have output current continuous, not the input current continuous, right? So in that case, how do you accomplish that? Okay, so um, how do you accomplish both input and output current continuous? So that is something that you will learn eventually. Okay. Okay, so I guess till this point, this is fine. So this is about your non-isolated DC-DC converters, right? So once we have studied about the non-isolated DC-DC converters, we can just move ahead to isolated DC-DC converters. Basically, we will study about two converters, that is the forward converter and what is known as the flyback converter. Okay. Okay, so just a second. It has become really hot over here, so I'll just have some water in the So we come to what is known as the forward converter, right? So you can understand the forward converter is kind of a bug-derived converter. The reason being that in the output side, right, between this to this is totally emulating a buck, correct? This is the output side of a buck converter. So just that in the input side, we are having an isolation, right? So that's the only difference over here. So this is a buck derived converter. You can understand that the output voltage will be what? N into dVi. So for a buck converter, it is D times Vi. But for a forward converter, you have to include the turns ratio of the transformer or the isolation stage. So V naught is N into dVi. So N is another control parameter that you have in your hands. But of course, once you fabricate the transformer, you cannot change N just like that, right? So again, the controlling parameter will be D. Okay. So again, I'm not going through the entire process, but point is you went through all the waveforms over here regarding what will be your VA, and that is the pole voltage, right? So you can understand pole voltage is somewhat similar to the buck, but just that instead of VI and 0, you have N times VI and 0, right? It is NVI because of the isolation stage, right? And across the inductor, the voltage will vary between, for buck converter, it was Vi minus V naught to minus V naught. Here you have NVI minus V naught to minus V naught. Again, the NVI is coming only because of the isolation part. Okay. So when the switch is turned on, so there is a path over here through this. So the entire V in will appear across your primary side, that will get transferred to the secondary side as N times V in, and that is what forward biases this diode and appears over here. Okay. And one more thing is we have to provide a path for the flux to actually go back to zero, right? And that is what is known as a demagnetizing path over here, correct? So during the 1 minus dTs period, that is when the inductor is freewheeling through this diode, then what you want to do is you want to demagnetize the inductor so that the inductor doesn't saturate, correct? You want to demagnetize it, you want to bring the flux back to zero, right? You have to do flux resetting, right? So that is why you provide this shunt path through this diode and RM. Okay, so this diode will ensure that there is only unidirectional current flow, that is only in the reverse direction. Correct. So the stored energy in this inductor will dissipate through RM. Okay, right. So again, you went through what is the switch rating and all. That is the current through IQ and the current through the diodes and all, right? Okay. So yeah, as I was talking about it, you have the core resetting point over here. That is, you want to make the IP mag back to zero, right? It obviously the magnetizing current would increase during the DTS period when the device is turned on. And what you do is you will have an LR circuit over here, and you will bring it back to zero. Correct. Okay, and because of this extra expenditure that you're going to make, what you will see is the blocking voltage is actually higher, right? The blocking voltage is not only Vi. If you apply KVL over here, the blocking voltage will be Vi plus VDM plus IMRM, correct? So not only Vi, VDM plus IMRM plus Vi. So your device needs to be rated for a much higher voltage than Vi. Not in a buck converter, the device is rated just for Vi. Correct? In a buck converter, the device is rated just for Vi. But here you see that the device has to be rated for a much higher voltage because of this demagnetizing path. Right? But the advantage is the flux resetting will happen, core reset will happen. And you also studied how to size these values of RM and DM, correct? So it is based on the time constant, that is you want the flux to decay back to almost zero, right? In the 1 minute DTS period, you want the flux to decay back to zero. So that is why you want the 5 tau, the settling time, to be much, much faster than your 1 minute DTS period. Mr. Tyagarajan, can you please mute yourself? Mr. Tyagarajan, can you please mute yourself? Okay. Okay. So one thing is, because if you want to have proper flux resetting, you need to ensure that the flux core gets reset within this 1 minute t period. So your time constant or phi tau should be less than or equal to 1 minute dts period, right? So that defines your value of Rm. And secondly, you should also choose the device so that the device rating is not exceeded, right? So this is just based on the KVL expression. So this gives you the limit of Rm within which you can choose. Okay, within which you need to choose. Okay, and of course the resistor should not be some signal level resistor. It should be rated for power dissipation, because you understand that whatever energy is stored in this LM or whatever energy is stored in the core is going to get dissipated across RM. So the power rating of the resistor should also be high. You should select a resistor with suitable wattage rating, right? So this is the selection of resistor, that is, it should be doing flux resetting within this 1 minute d period. And secondly, you should choose a resistor so that the blocking voltage is also satisfied from the data sheet of the device. Okay, and obviously the resistor needs to be rated for suitable wattage. So you understand that this is kind of a lossy thing that you are having over here, that you dissipate the energy through resistor, right? So instead of that, what can I do? So instead of that, can I have a demagnetizing winding? That is, I will transfer whatever is stored energy to this winding, right? Or to this reset winding. So that is what we do. That is, we have a kind of a demagnetizing winding, or what is known as a reset winding, in an opposite sense. That is, you can see that the dot polarity is opposite over here, right? So during the 1 minute d period, simply I will circulate the current through this demagnetizing winding. Okay. So since the demagnetizing winding is in no way connected to the output side, I don't care about it, right? So I will just circulate the current through the demagnetizing winding. And of course, there is a diode over here to ensure that the current is only unidirectional and it cannot be bidirectional. Okay. Okay. So this was about the forward converter, right? So forward converter, as you can understand, was a buck-derived converter. We saw its waveforms, and we also saw the problem of core reset over here. And how do we choose the value for RM so that core reset happens properly and also the device rating is not exceeded. And another thing is we have the demagnetizing winding. So apart from that, we move on to the flyback converter. Correct. So flyback converter is kind of derived from the buck converter, buck boost converter, as shown over here. This is a buck boost converter, and you understand that the V naught is going to be minus dV 1 minus dV in, right? So this is a buck boost converter, and over here we have. Okay, so before I proceed, I think I forgot to mention over here what is the voltage and input and output voltage relationships. So V naught over V in, right? For a buck boost converter is going to be 1 by 1 minus D, and over here it will be, sorry, it will be minus D by 1 minus D, correct? Okay, so this is the input output relationship. So you can understand that, and for a buck converter, V naught is equal to dV in. So as D increases, right, as your switch is on for more and more period of time, your V naught increases in a buck converter, but if your D increases in your boost converter also, you can understand that if your D increases, then 1 minus D is going to be lesser, therefore 1 by that lesser value will be very high. So your V naught again increases if your D increases. Correct? Okay. And for this buck boost converter, it will be maximum at, I mean, there is this point at 0.5, at D is equal to 0.5. So if your D is lesser than that or greater than that, it will be varying, like you can plot, right? Okay. Yeah, so we were over here with flyback converters, and as I was talking about that, it is derived from a buck boost converter. wherein you have this relationship. So in this inductor part, can I induce an isolation stage in near this inductor part? Correct. So that is what we have done over here. So unlike the forward converter, in forward converter you have a separate inductor, correct? Just the isolation is being provided by a transformer. But over here you understand that this entire inductor is being replaced by a transformer, correct? So that is why in a flyback converter we generally don't call it as a transformer. We call it as a flyback transformer or a coupled inductor. Okay, this is still the inductor. This is still functioning like an inductor, okay, not like a transformer, correct? So in a flyback converter, we call it as a coupled inductor. The reason is because just in this inductor, we have replaced the inductor so that we get an isolation, right? So, but still this is acting like a coupled inductor and it is providing isolation like a transformer. So there is no separate inductor as such. It is just the isolation stage itself that is functioning like an inductor, right? Okay, and of course you can understand the secondary side is similar to a buck boost converter from this diode on, and this is the inductor and this is the actual switch. Okay, so you went through the operation and all. I'm not going through the operation once again, but you can understand during the duty period when Q is on, then there will be a direct path over here. Therefore, Vp is equal to V in during that interval. Correct? Vp will be equal to V in during that interval. Since Vp is equal to V in, Vs would be equal to minus n V in because the dot polarity is opposite. There Vs would be equal to minus n V in. The D is reverse biased. Therefore, the capacitor will feed the load. Okay, capacitor will feed the load, and this inductor will charge up. When you turn off the device Q, then what would happen is basically there is going to be this inductor is going to discharge through the output side. Okay, so this diode will be automatically reverse biased, so the current will flow like this. Okay, yeah. So that is why you see over here the IC current is equal to IL minus I naught or ID minus I naught during the 1 minute D period and minus I naught during the D period. During the DTS period, Q is on and the diode is off. So capacitor discharges to load, so IC equal to minus I naught. When during 1 minute D period, Q is off, so there is a current ID, so IC is equal to ID minus I naught. And since ID is same as your inductor current, inductor is kind of decreasing during this period, therefore ID minus I naught is also decreasing. Right? Makes sense, right? Okay, so based on this, you can find out what should be the device currents for Q and D and what should be the voltages, and based on that, you can rate the device as suitably. But one thing or one drawback is if you see the voltage stress on the device Q, right? It will not be simply VI, it will be VI plus V naught over N, right? That is when the device is off, then what would happen is the diode is forward biased, therefore V naught is going to appear over here, right? V naught is appearing over here, it gets transferred to the primary side as V naught over N, therefore the total voltage will be VI plus V naught over N, right? So the device needs to be rated for a much higher value than VI. And similarly for the diode, if you see the peak inverse voltage, when the diode is off and when Q is on, VI will come over here as NVI, and this is already V naught. So you will see that the total voltage is going to be NVI plus V naught. It is plus because the dot polarity is opposite, right? So it will be minus NVI over here and we have minus V naught over here, correct? So yeah, so till this point, is it fine? So in this isolated converters, we have studied two, it is forward and flyback. Forward is kind of your forward is kind of a buck derived converter, and flyback is kind of your buck boost derived converter, right? And we have seen both of their operations. Okay, so actually I will stop till this point. Still there is this magnetics part. I think you can go through this. I think we have covered this very recently. So you can go through the brief steps over here, and push-pull converter and the drive circuits were just covered in this week and the previous week, just some 7 days earlier. So I think they will relatively be fresh, but still the slides are given over here. If you want, you can go through that. But for this session, I think I can stop over here. Okay. So till now we have seen the three devices, then the AC-DC converters, AC-DC converter operation, interest current limiting, different types, and then the linear DC-DC regulators, that is the series and shunt regulators, and then the non-isolated converters, namely the buck boost and buck boost converters, and then the isolated playback and forward. Okay, isolated converters, playback and forward. And for each of these, we have seen multiple problems throughout our sessions. You can go through the lecture slides. We have seen almost around 17 or 18 problems for each of these. So you can go through the lecture slides for that. And yeah, so still magnetics, and then your push-pull, half-bridge and full-bridge converters, as well as the drive circuits are there. And of course, in the next week, we will see about the control algorithms. So, but I will stop here for now. And if you have any doubts, you can ask now, or like we can close for the day. Okay, so thank you very much for attending, sir. Yeah, so have a great week ahead. I will stop sharing now. I'm not able to hear you actually. Okay. Sorry, your voice is totally not audible. Can you please type? Can you please type? Okay, thank you very much for attending. Yeah. Okay, so have a great week ahead. I will close over here and good night and bye.